Our next talk is lighting technology of The Last of Us. This talk will be presented by Michał Iwanicki. So he's a game programmer with 10 years of experience. He started in Poland in 2003 on The Witcher for CD Projekt Red. Then he became the lead engine programmer for CD Projekt Red and worked on the technology for all of their games through 2009 when he moved to Guildford and Lionhead Studios to work on Milo and Kate. Presented some work related to that project at GDC, though that project didn't ship. Since 2011, he's been at Naughty Dog and has been working on The Last of Us, which did and has been quite successful, and he's going to present some of the lighting technology from that title.
Thanks for the introduction. Here we go. Okay, so the talk is titled Lighting Technology of The Last of Us, but I should have called it Old Lightmaps, New Tricks. But I just thought that if I put the name of the game in the title, more people will show up, and it kind of worked. So, The Last of Us is an action-adventure survival horror game from Naughty Dog. There's a heavy emphasis on storyline characters. It takes place in a post-apocalyptic world, and the mankind has been decimated by a mind-controlling fungus. But if you haven't seen the game yet, here's a short trailer for you. So yeah, it takes place in a post-apocalyptic world. There is no electricity, which means there are almost no artificial light sources. The majority of the lighting comes from sun, sky, and most of the interiors are lit just by indirect illumination, just the bounce lighting. And there was a very strong art direction. We wanted to show the beauty of this lighting, how it interacts with different surfaces, how it creates nice specular highlights, how it creates soft shadows. And just to give you an overview of what we were after, here's some concept art. So as you can see, all the lighting is very soft, but you still get a very clear read of all the surface details. So from the very beginning, we knew that to achieve that level of quality, relying purely on runtime illumination will not be enough, that we needed to pre-compute our lighting, and we decided to use lightmaps for this. The problem with lightmaps is that even though they have been in use for years now, like since Quake 1, I imagine, they still suffer from some very basic problems. Like the seams, for example. The discontinuities in the lighting, just like here on the image on the right. It can happen that the parts of the image that are continuous in 3D space are being mapped into two disjoint regions in UV space. And the interpolated values along such split edges don't quite match, which causes a visible discontinuity. And while there are some methods to deal with those issues, they are pretty restrictive on how the charts are being placed in the UV space, or how they are shaped in UV space, or they impose some restrictions on how we perform the lookup in the lightmap, making it more costly. And this was something we needed to avoid just because we wanted to get the most of the platform. So we found pretty simple yet effective solution. So if the interpolated values don't quite match, let's just make them match by slightly modifying the texels that actually influence them. So this is how it works. We have a mesh in 3D space here on the left, and it's being mapped into UV space on the right into two disjoint regions. And along the edge that is split, we create a number of what we call stitching points. And let's investigate what's going on in one of those stitching points. So the value on the chart on the left in a stitching point is the interpolated value of 4 surrounding texels, marked in blue here. And it's the same for the value on the right chart. It's just the interpolated value of 4 surrounding texels. We're using bilinear interpolation for the light maps. And what we want, to avoid any discontinuities, we want those two values to be equal. So we define an error function that is a squared difference between those two values. And later, we define an error function for the whole light map as a sum of error functions for individual stitching points. And once we have an error function, we can just minimize it using least squares, treating the texel values as variables. The optimization modifies the texel values slightly and makes sure that the total error is minimized, making sure that there are no discontinuities visible. And to make sure that the values of the texels don't deviate from the originally calculated ones, we add some additional constraints for this with a user controllable strength. And this works remarkably well because we don't have to do any changes to the UV layout. We don't have any additional runtime cost. Can also be used in different applications, like, for example, just stitching diffuse albedo maps or even displacement maps. Oops. There are some caveats, however. DXC compression tends to break it up a bit. You can either live with it, because in most cases it just looks pretty okay, but when it doesn't, we have an option to restitch it after decompression, this time modifying blocks anchor points instead of individual pixels. The second thing is the linear solver you use for the optimization. Just don't write your own. It's a very bad idea because there are pretty good ones available. There is Eigen, which is totally awesome because it comes as a collection of header files. So if you don't like the hassle of integrating big libraries, this is something super useful. You just include a bunch of header files and you're done. This is one small off-topic slide. I just hijacked it, but I had to say it. Just add least square minimization to your bag of tricks. It's super useful, but it's often overlooked, especially in a game developers community. Because once you use it, you suddenly see tons of other applications for it. Like, for example, let's take a look at typical pipeline for 3D lookup tables that are used for color corrections in game. So the way it usually works is you take a screenshot in your game, like here, then you embed an identity volume texture at the very top of the image. Then you take this into Photoshop, do some massaging, you get a nice color correction, and then you extract the volume texture to be used in game. And later at runtime, you render your scene as usual, and you apply the volume texture to get the same result you got in Photoshop. Well, the problem is that the result in the game is not exactly the same as the image in Photoshop. Because of the low resolution of the volume texture and the quantization of different components on the way, you can get some pretty serious discolorations. This was actually the first thing we heard from our concept artists when we put this technology in. Well, it doesn't look the same as in Photoshop. Well, really? So we investigated and we realized, yeah, they're just not the same. So what we can do, we just minimize this difference with a least squares methods. So we define an error function as a square difference between those two images, and we optimize it to make it as small as possible, modifying the volume texture. And it works really well, looks much better than just using the volume texture as is. So just, least squares. But going back to the lighting. We wanted to avoid the flat look of our surfaces in the absence of direct illumination, so we knew that we needed some sort of directional information in our light maps. So some options we evaluated were Half-Life 2 bases, We tried spherical harmonic light maps, but we settled for very simple representation of a pair of ambient and directional lights that stored per lightmap texel. This gives us some really nice properties. First of all, it's really easy to understand by the artists, which is extremely useful property because they tend to investigate the outputs from the baked process. What else? It can be hand-tweaked. For example, if we need to modify the direction, the dominant light direction slightly, it can be done. And we have this direction, which we can use for different purposes, like to add specular reflections. So the way it works, our global illumination tool just gives us some distribution of the incoming lighting per lightmap texel, like here. And we take this and we divide it into an ambient term, which is just a color of uniform lighting arriving from all the directions, and a directional term, which is a direction, and a color again, which is the intensity of the lighting arriving just from this direction. And we generate this representation from an SH light map, which is generated by our bake tool. And we do it in a way that minimizes the difference between the lighting produced by those two representations. So light maps can now be used with normal maps to provide high-frequency details. So the diffuse lighting is simply the ambient term plus directional terms times n.l. And like I said before, we can use this direction to add specular reflection according to the surface BRDF. And this works really nice. We have a nice-looking background, normal map details, specular reflections. We don't have any seams, and then we add characters. So this is the background, and then we add characters, and it suddenly looks just bad. The characters looks like if it was a sticker on a screen rather than something, fitting into the world. What we actually want is this: the character that is nicely grounded, that casts nice soft shadows, that looks like if it's actually part of the environment, like if the lighting actually influence him and he blocks the lighting. He's not something just added later on. So the original inspiration how to solve this problem came from SH exponentiation papers. So what they do, they approximate dynamic occluders with a set of spheres, and they accumulate the visibility function from each of those spheres by multiplying SH representations in a fancy way. The problem for us was that to get some decent quality and nice long shadows, you need a really high SH order. Just second order SH just doesn't work because it's nice for AO, and Stephen Hill did something similar in splinter cell conviction, but to get long soft shadows, you just need more. But we need to remember that we decided to use a very simple representation of our visibility of our lighting structure. So we don't need the whole visibility function. We can just figure out how to occlude those two components appropriately because we've got an ambient component and a directional component. So just like the papers I mentioned, we approximate our occluders with spheres. And for each such sphere, we occlude each of the component of the incoming lighting separately. So the ambient component is occluded. The occlusion is calculated as a cosine-weighted percentage of the hemisphere that is occluded by the occluder. And for the directional component, we trace a cone from the point that is being shaded along the light direction and check for the intersections with the occluder sphere. So here's the breakdown of how this works. We have a point in space and certain distribution of lighting, and we have an occluder marked in gray here. And for the ambient term, we just check what part of the hemisphere is subtended by the occluder. And for the directional term, we cast a cone along the direction of the dominant light and check what part of this cone is occluded by the occluder. So here's a short video of how this works in practice. This is the thing with the technique turned off. As you can see, if there is no direct illumination, until the character comes into the direct sunlight, it's basically you don't get any clues about his position in space. It looks like just something floating above. And when we enable this technique, we get a soft shadows being cast along the direction of the light. I think the video is being cropped a bit. But yeah, it casts shadows on all the surfaces around. It's not just the ground. It looks like if it's actually part of the world, not just something added later on. Okay. So now for some technical details. So for the ambient term, for the occlusion of the ambient term, there is a closed form solution for the occlusion value, because it's just the integral of the angle of the cosine lobe over the angle subtended by the occluder divided by the cosine lobe integrated over the whole hemisphere. For the directional component, there is a closed form solution for the occlusion term as well, but it's rather cumbersome. So we found out that it's much easier just to pre-compute it and store it in a texture. Since for a given cone angle, the value of the occlusion is just a function of a angle subtended by the occluder and the angle between the cone axis and a vector pointing towards the center of the occluder, so just theta and phi in the diagram here. We can pre-compute it and store it in a two-dimensional texture. And for multiple different cone angles, we can just stack multiple of those textures in a 3D texture. So the cone angle we use for the tracing is chosen arbitrarily. It controls the penumbra size. You can see the results for different cone angles here. And we exposed it to our artists. They control it on per level basis, but there is absolutely nothing preventing us from using a different angle even for every pixel on a screen. For multiple occluders, we accumulate the results of both intersection tests in screen space by multiplying the individual results. This is not 100% accurate, and in theory it can result in double occlusion, but in practice it's totally not visible. I don't see it even though I know what to look for. So here's some more low-level details about how it works. So we start by rendering the dominant light direction to an off-screen buffer. This is what it looks like. And this is later passed to the SPUs together with the description of the occluders. And then the SPUs divide the whole image into tiles and process each tile in a separate job. So we start by calculating which occluders influence each tile. So each occluder has what we call sphere of influence, so it casts shadows only within a certain radius. And at the very beginning, we just check for intersections between those spheres of influence and the tiles. It's pretty similar to how you do the culling of lights in tile-deferred render. The thing is that the occluders are pretty large compared to the tile size. So if you use a regular test between frustum and a sphere, you get a lot of false positive, which we didn't want. So we do it in a bit different way. We first calculate the view space bounding volume of all the pixels within a tile, and we compute an intersection between a three-dimensional bounding box of those pixels and a sphere, which is much tighter test and gives us much better results. We get just less spheres to test. And once we have the spheres that influence given tile, we just compute the occlusion factors and we store it in a texture. This is this texture. And this texture is later passed to the GPU, which uses it in a main rendering pass to produce the final image, just to occlude the individual components of the light map. Here's basically the same thing, just written down. And for like 6-7 characters on screen, 4 characters on screen, which is our average, it takes around 6-7 milliseconds, but it's distributed onto 6 SPUs, so the results are usually ready in less than 2 milliseconds. And the GPU is doing some work in the meantime anyway, so it's not waiting for the results. So to speed things up, we introduced a scaled sphere as an occluder. It's basically just a sphere scaled along one axis. And when we do the intersection tests, we basically scale the sphere down, scale the ellipsoid down to a sphere, scale the direction as well of the cone. The thing is that we don't scale the cone itself. We still use the regular non-squashed cone, which is not accurate, but saves us a lot of performance because we can use lower number of spheres. Then we render the whole thing in quarter resolution. Because the shadows are really soft, it works really well. You don't really see the problems with it. We have an option to perform bilateral filtering on per object basis because most of the objects just use the result as is. But it's used very sparingly since it's a bit too costly for us. And lastly, some objects can require too many spheres to approximate, and for those we support pre-computing the occlusion and storing it in a 3D texture. And the occlusion for those objects is just applied on top of the regular ones. So just to conclude, the pre-computed lighting is definitely not dead yet. You can use relatively simple tricks to make it look much better. And don't forget about least square minimization, and don't write your own solver for this. And thank you for your attention. And if you have any questions, please feel free to come to the mic.
Thank you for a very nice talk. When we played The Last of Us, we've noticed there was, besides of some static light GI, we've noticed some dynamic GI, for example, from characters' flashlights.
Yes.
So can you tell us which technique do you use for that?
The character's flashlight use reflective shadow map, and actually this is work by Kay Shrew, who's sitting over there, so he can probably give some more details about it.
Thank you so much again.
Sure.
When the directions change because of a shadow for the directional light map, how do you keep them consistent with
so it's a very good question actually. There's some information on the bonus slides. I just didn't show it. So the thing we do, the dominant light direction tends to change quite a bit on the shadow boundaries. What we perform a basically low pass spatial filtering, just blur the hell out of it. The thing is that we first extract the direction, then we blur it, and then we extract the lighting values. So we keep the same energy, it's just distributed differently between ambient and directional terms.
Thank you.
Well, thanks a lot.